Chapter 8.4 on the Properties of Logarithms. Now this is sort of interesting. Logarithms are basically a new operation. Like add, subtract, multiply, divide. It's essentially a new type of operation. So we've got powers, which is 2 to the third equals 8 because it's 2 times 2 times 2. That's repeated multiplication. Well, logarithms are the inverses of these powers. So let's go back and think about multiplication. 3 times 4 is repeated addition. We'll call that 4 plus 4 plus 4. I should have done 4 threes, but whatever. But division, 12 divided by 3, can be thought of as repeated subtraction. That's fine. But you can also think of it as just the inverse of multiplication, meaning, okay, if 12 divided by 3, what number times 3 equals 12? And that was 4. Well, here's the power version. The logarithm is the inverse of that power. 3 to what power, 2 to what power equals 8 is the question here in 3. So it's essentially like we have a new operation, and that provides us with a new set of properties that are very closely related to the properties of exponentials because logarithms are exponentials. Two properties we've actually seen before, at least I think we have. I guess maybe not explicitly like this. If you have log base b of b to the x, you're just going to get x. And this just comes from converting. Like say we had log base 3 of 3 to the 5th. Well, if this base and this base of this input, if those are the same, they're going to cancel because you're asking the question 3 to what power equals 3 to the 5th? So the question really is, if we convert into exponential form, 3 to what power equals 3 to the 5th? Well, obviously the power is 5, so x would be 5. So this comes from converting. If the bases here are the same, essentially you can say these two things undo each other and you just get x. The same version in the other form is if you have b to the log base b of x, you just get x. So like 4 to the log base 4 of 16. Well, I could convert this from what right now it's an exponential form. I can convert it into log form. So the log is base 4. So it's log base 4 of x equals log base 4 of 16. Well, then obviously x must be 16. So this just kind of copies to here. We can even show that simpler. We can just calculate log base 4 of 16 is 2. 4 to the second is 16. These two properties are super useful. We're going to rely on them a ton when it comes to solving. So the key to all of these properties is if you have the common base, then the log and the base cancel each other with that exponential. Here's 3 more properties of logs. On the left side, I have properties of exponents, just to remind us of how these work. And these are actually written in a way that you don't usually see. Usually this order is flipped. You would say b to the x times b to the y equals b to the x plus y, right? Like 3 to the 4th times 3 to the 5th is really 3 to the 9th. I have it written in this backwards form to show kind of the symmetry of how this relates to properties of logs. Go away, arrows. Over here, if you have log base b of x plus log base b of y, the inputs combine and multiply, so it's log base b of x times y. Addition became multiplication, just like how here addition was from this multiplication. If you have log base b of x minus log base b of y, it's log base b of x divided by y. Subtraction becomes division, just like here the subtraction became division. If you have log base b of x times y, that's the whole same as, sorry, not log, just b to the x times y. That's the same as b to the x to the y. Well, this property here is the oddest and possibly the most useful, the one that we'll rely on the most when it comes to solving. If you have multipliers in front, they can move up to the top and become powers. And we'll actually see this more often in the other direction. If I have like log base 3 of 4 to the 5th, by this property, this power can come out in front and become a multiplier, 5 times log base 3 of 4. It's a little bit tough to explain why this one works the way that it does. It's basically because logarithms are having us count powers. It counts change in the powers. And change is really a multiplication question. So a power of 5 is 5 changes to the power. But these are the 3 properties of logs. This one here on the bottom is one that is very odd, but very wonderful. So I'm going to simplify these real quick just to show how this can work. Here's log base 3 of 8 plus log base 3 of 5. They have the same base and they're being added, so the inputs are going to multiply, and I get log, okay, I can write log base 3 of 40. And that's simplified. We're down to just one log expression without coefficients. Here, these have the same base. Subtraction becomes division, so it's going to be 20 divided by 4, and it's log base 0.9 of 5. I simplified that down to one single expression. That's the goal. This one has coefficients, so I can use this property of logs and pull this up as a power and pull this up as a power. So it becomes the log of x to the 4th minus the log of x squared. Now, subtraction becomes division, so it's log of x to the 4th divided by x squared, which is log of x squared. Some of you might have actually noticed, though, that these are like terms. And I can just subtract 4 log x minus 2 log x is going to be 2 log x. And the 2 comes up as a power, and it's log of x squared again. Notice that those are the same. Great. Either way is fine. It's beautiful. I'll switch colors for this last one because I'm starting to get kind of deja vu'd. These, however, are not the same inputs. So I can't just do 12 minus 3 minus 4. All those things aren't working out the same. Remember, the base here is 10. If there's no base written, it's called the common log. And we just know the base is 10. The assumption is you're doing base 10. So I'm going to pull up these coefficients as powers first. After I pull up the coefficients as powers, then I'm going to simplify with a bunch of division, because subtraction means division. So 12 comes up as a power, 3 comes up as a power. If you wanted to pull up negative 3 as a power and make this addition, you could. I just don't tend to do that. So this becomes the log of x to the 12th minus the log of y to the 3rd minus the log of x to the 4th, y to the 4th. Both of those things are brought to the 4th power. Now, this subtraction makes division. This subtraction also makes division. There's kind of two ways you can think about this. One of them is everything that's negative goes on the bottom. Everything that was positive goes on top. This is a positive log. These two are negatives. So I'm going to have the log of one big parenthesis, x to the 12th on the bottom. I'm sorry, on top. Y to the 3rd, x to the 4th, y to the 4th on the bottom. So this is now x to the 12th over x to the 4th, y to the 7th. And then these x's can simplify. So it's the log of x to the 8th over y to the 7th. Positive things were on top, negative things were on the bottom, and I simplified. I could also just do division. I said there's two ways. The second way to do it is just divide. X to the 12th divided by y to the 3rd, which is divided again by x to the 4th, y to the 4th. And I'm showing you this, even though I think it's a bit more confusing and complicated, because it's worth remembering how to do division of division. The bottom thing is going to flip and multiply. So think of this like it's x to the 4th, y to the 4th over 1. It's going to flip and multiply. So we now have log of x to the 12th over y to the 3rd times x to the 4th, 1 over x to the 4th, y to the 4th, which will simplify to this. They end up being the same thing. All right, like this thing here is real similar to this thing here. So that's simplifying with those three properties of logs. Useful for eventually. Here's a final property that we've actually talked about a couple times with graphing and evaluating. It's called the change of base property. If you have a fancy calculator, you won't be using this one, but it's still worth understanding. Here's log base b of a. That becomes the log of a divided by the log of b. That's the change of base formula. So if I had like log base 3 of 12 in my calculator, I could type in log of 12 divided by log of 3. Now technically I could change the base to anything. We always change to base 10, but I could change to base 5 or 8 or 2 if I wanted. The formula usually has little C's written down here, meaning you could pick any base you want to change to. It's just we always change to base 10, so I don't see why bother. Well, base 10 or base E, which that might make no sense to you, so hang on for 2 more videos. So where does this property come from? Let's say that we had log base b of a. Well, what I can do is I can just call this x. And I get b to the x equals a. Then the tricky little bit you're going to start seeing is I can take a logarithm of both sides. Just the logarithm of b to the x equals log of a. The x comes out in front as a multiplier. I can divide both sides by log b. And that gets me x equals log of a divided by log of b. So there is the change of base formula. So here are all 6 of our logarithm properties written down in one space if you'd like to copy them down. I'll say what I've said before, which is just screenshotting this is not going to be sufficient. You need to actually be writing this stuff down so that your fingers have a chance to experience it and so it passes through your brain. If you just screenshot it, you bypass all of you, right? It goes from my video to your phone or iPad or computer or whatever, but doesn't actually like go to your brain or your fingers, and that's a problem. So write these down so that you have at least some basis of understanding for them. Now this helps us with solving exponential problems finally. I am going to do that same trick I pulled before where I can have 4 to the x equals 40. The idea here is if this is a true statement, if 4 to the x actually equals 40, then this is also going to be a true statement. The log of 4 to the x is going to equal the log of 40. I'm just taking a log of both sides. Now our property, let's pull this x out in front. So x times the log of 4 equals the log of 40. I can then divide both sides by the log of 4 because the log of 4 is just some number. You know, it's some number where 10 to some power equals 4, so it's a very small number, but it's just some number. And we get x equals the log of 40 divided by the log of 4. Now this is something that I could plug into my calculator and actually calculate, which we've not been able to do for a while. So this is a pretty big deal for us. I am not going to actually plug it in right now because I'm just going to keep going. So here I want to solve this. I'm going to get this power of x by itself. First subtract the 4 from both sides. So negative 2 times 3 to the x equals 1. Divide both sides by negative 2. And you get 3 to the x equals negative 1/2. Again, take a log of both sides. Log of 3 to the x equals log of negative 1/2. The other option, if you don't want to take a log of both sides because maybe your computer can't actually write, there's 1/2, negative 1/2. The other option is I could just convert to log form. Log base 3 of 1/2 of negative 1/2 equals 2 equals x. But I'll stick with this. I'm going to pull this x out in front. So it's x times the log of 3 equals the log of negative 1/2. Divide both sides by the log of 3. and you get something. Although in this case, the something you get is it's not possible because you can't have a log of a negative number. So this equation wasn't going to be solvable to begin with because 3 can't equal a negative 1/2. Hey, thanks for watching. Cosine wave. Here it goes. Bang. Back and forth. Back and forth. Like, subscribe, share, tweet. I don't know. Do you guys still tweet? Is tweeting still a thing? I made this in 2017, and by now, for all I know, it's like 2035, and you're still watching my math videos, because math doesn't change that much. What are you doing now? Are you like connected to the hive mind? You've probably got like antennas implanted behind your ear that connects you to the hive mind that tells you what to do at all times. Resist, fight. Just because iPhone sells it to you doesn't mean you need it. I don't know what I'm talking about.